Welcome back to the series of lectures on high-performance scientific computing. So far, we have looked at the basics of distributed memory machines and how to program them using MPI. We had discussed some simple examples of sending and receiving messages and how to build programs based on that. Today, we will go a little bit further into MPI and talk a little bit more about the other functionality that MPI offers and how communication can be enhanced between different MPI processes. What we will especially look at is collective operations in MPI. So essentially in collective operations, what happens is that all processes, i.e. all rank numbers in a communicator, are called together. For example, you have the MPI broadcast function. It takes the data from one process and sends it to all the other processes within the communication world or the communicator. Now, this process can be sent from typically the root that makes it things simple in terms of an algorithm, but it need not be restricted to be sent only from the root process. In theory, any process can do an MPI broadcast and communicate data to all the other processes. Now, in the event you did not have access to an MPI broadcast function, you will have to do several pairs of MPI sends and receives. Similarly, there are other functions which were analogous to the reduction clauses in OpenMP, where you have MPI reduce, which combines data from all the processes in a communicator and returns it to one particular process. So, in most algorithms, a lot of sends and receives can be replaced by broadcast and reduce. This improves the simplicity of the programming and also increases the efficiency, because whenever you have multiple sends and receives which are not done in the broadcast or reduce framework, the MPI environment has to allocate different bits of memory for sending data for each of the pairwise communication. In this case, when you use a broadcast or a reduction clause, what essentially happens is that the amount of memory that is allocated and the buffers that are needed are fewer, hence improving the computational efficiency. So typically, the communication and computation is coordinated amongst a group of processes or ranks. That's how most calculations are done. But when you're doing collective communication, you do not use any tags. Different communicators will deliver similar functionality. You can also have non-blocking collective operations. We will talk about what non-blocking communications are in a little bit. So essentially, there are three classes of operations that you need to do. One is synchronization, two, data movement, and then collective computation. Finally, for synchronization, if we want all the MPI processes or ranks to come and synchronize at a particular point in the program, you would use the function MPI barrier. A process will not go ahead of the barrier when it is written down in a program until all the other processes have reached that particular barrier. How does collective data movement occur? So let us take an example that there are 4 different unique processes which are running, P0 to P3. They are also color coded and they have certain memory or data allocated to them. And you wanted to transmit the variable A to different memory locations of these different processes, or rather the first memory location of a particular array of different processes. So if you look at the MPI broadcast function, what you would do is that you would give the memory location where the data needs to be copied to and the source, and obviously what is the root process. In this case, the root process is the process P0, and the variable A then gets copied to all the other processes P1, P2 and P3 and is put in the first memory location of each of those processes. Now, instead of using the MPI broadcast functionality, if I had chosen to use the MPI send and receive, I would have had to have 3 MPI sends and correspondingly 3 MPI receives, increasing my program complexity. Apart from increasing the program complexity, I would have also need to initialize 3 send buffers. So whenever there is a communication which is taking place between 2 processes, the data is copied from the memory of the host from which the data is being sent to a temporary buffer, and from that buffer it is then copied over the network to the buffer, to the receiving buffer of the other process, and then copied from the buffer to the actual memory location. On the receive side, the number of buffers that are required will not change when you have the broadcast function. But on the send side, you will not have multiple send buffers, rather you'll have just one buffer to send, and all the other processes will try to take the data from that particular buffer. Similarly, there are other collective communication patterns which you would like to have. One is typically a scatter sort of an arrangement. Let us again assume that there are 4 processes P0 to P3, and you have a vector which is 4 long, and you have 4 elements stored in that vector A, B, C and D. Now you want to equally portion this vector amongst all the processes, i.e. you want to scatter this vector. So if you use the MPI scatter functionality, what it would do is that it would keep A in the first memory location of P0, it would transfer B to the first memory location of P1, transfer C to the first memory location of P2 and transfer D to the first memory location of P3. This is the scatter operation, which takes data from the process P0 and equally distributes it amongst the 4 processes P0 to P3. Similarly, you have a reverse process, which is the gather process. In gather process, you have 4 different data members lying in 4 different processes, which are 0 to 3. The data members A, B, C and D are in different processes, and the gather process collects all of them and puts them sequentially in the process P0. So this is the equivalent gather process. If we had to do the scatter process, again, if we had to do it using a pair of send and receives, which was eminently achievable, you would again have to have 3 sends and receives. Similarly, for the gather, you would have also had to have 3 sends and receives. Now, if you want to have an all gather, essentially what we are doing is that we are gathering all the data at one place, and then we are broadcasting it to each and every process. So if you look at the all gather functionality, what is happening is that you have data which is distributed from P0 to P3, A, B, C and D respectively. They are all gathered together in one location and then broadcast to each and every process. At the end of it, each of the processes have all the copies of A, B, C and D. This is an all gather function. If you actually had to do it by sends and receives, it is very clear that you had to do an sort of an all-to-all communication where P0 would have had to communicate A to P1, P2 and P3. P1 would have had to communicate B to P0, P2 and P3. C would have had to be communicated from P2 to P0, P1 and P3, and hence D would have to be communicated to P0, P1 and P2. So this would have resulted in 12 sends and receives correspondingly. So the all gather function does it together in one shot. All the sends and receives are hidden from the user, making it easier from the programmatic perspective. Another version of this is something called as an all-to-all. So if you look at an all-to-all communication, let's say that you had a vector A0, A1, A2 and A3 which is resident in process P0. Similarly, you had B0 to B3 in process P1, C0 to C3 in process P2, D0 to D3 in process P3. At the end of all-to-all communication, what essentially is happening is that there is an exchange of data from different processes to its corresponding vectors. So, for example, you have data which is moved from P1 which is B0 to the process P0. Similarly, P2 moves C0 from P2 to P0 and P3 moves D0 from P3 to P0. So, the way this looks like is that all the data members which have the subindices 0 will be in process P0 at the end of the communication, 1 will be with P1, 2 with P2 and 3 with P3. Essentially, this looks like having a transpose of the matrix. So, what we are doing here is essentially first gathering data and then rescattering data in a different order, and that is essentially an all-to-all communication. You can look at the graphical representation to get a clearer idea of how this is done. We can also have reduction functions. So, in reduction functions, what we are essentially doing is that we are collecting the different data members from different processes and reducing it using some sort of function. This function could be doing a summation, doing a product, doing a maximum or a minimum. So, if you look at the reduction function, what it does is that it will loop over all the processes and then give out one particular result, which is a function of A, B, C and D. You can also have a slight variation to this, which is the scan function. So, if you're looking at the scan function, what it does is that it looks at it sort of progressively. So, if I want to do a sum reduction, let's take an example of doing sum reduction using the scan function. So, if I say MPI scan A, B, C, the process from the processes P0 to P3, for the first process P0, the scan function will return just the variable A. If I am doing a sum reduction for process P1, it will give me a sum of A and B. For the process P2, it will give me a sum of A, B and C. And for the process P3, it will give me a sum of A, B, C and D. So, you can think of it as doing partial sums sequentially. So, as you keep going higher in ranks, it is going to do more and more cumulative sums. So, that is the MPI scan function. So, there are many such MPI routines, more than 125 of them, and one can refer to the MPI manual to look at these collective routines. These are MPI all gather. MPI all gather V is the vector version for it. So, when you have different chunks of different sizes, you should be using all gather V. You have MPI all reduce, MPI all to all, MPI broadcast, MPI gather, MPI reduce and then scatter, MPI scan, MPI scatter vector, so on and so forth. So, all of these can take in user defined functions as well. So, what are the different collective computation operations that are available in MPI? So, you can take a maximum, you can take a minimum, you can take a product, you can take a sum, you can do a logical AND operation, a logical OR operation, a logical XOR, bitwise AND, bitwise OR, bitwise exclusive OR, and do a maximum and the location of the maximum, minimum and the location of the minimum. So, in which array member is the location, you will get to know. Similarly, you have non-blocking communication. So, if you look at non-blocking sends and receive, it basically does deadlock avoidance. What do we mean by that? If you have a send, you need to have a corresponding receive in another MPI process. Now, until this receive is done, the program at the other end will not proceed ahead. So, receives are blocking by nature, but the program would like to go ahead if the usage of that data is going to be only later in the program. So, you would like to overlap communication and computation. So, for that you would use non-blocking sends and receives, examples of which we will talk in future classes. So, when you are doing collective communication, they are also blocking by nature. Like for example, if I use an MPI broadcast, until the variable has been broadcast to all the respective processes and they have received the data, the programs will not advance. Now, it might be useful to overlap this communication with some computations if the broadcast variable is not required immediately. Hence, it is advisable to use non-blocking collective communication if your program is not critically dependent on the broadcast variable at that particular moment. This also has good advantages from a programming perspective because it increases the efficiency. Now, let us look at some regular mesh algorithms. Now, most scientific applications typically involve the solution of partial differential equations. Now, most of these algorithms approximate solutions of PDEs by forming a set of difference equations, usually employing some methods like finite difference, finite elements or finite volume. So, what these approximating solutions essentially do is that they turn these set of continuous partial differential equations into a set of algebraic equations. The form of these differential equations obviously depends on the particular method, but from a programmer's view, they are essentially the same, in the sense that they are a series of linear algebra equations, a set of simultaneous equations which we need to solve. And we need to typically solve them over a large number of unknowns. One of the popular approximations is called as the 5-point stencil. You will see this over and over again in two-dimensional problems of many different governing phenomena. So, let us see how does the 5-point stencil look from a computational perspective. So, if you look at the global data structure, in that each dot or circle is a mesh point or is a point where the concerned variable is being evaluated. Now, this concerned variable depends on the sort of physics that you are trying to solve. For example, in the steady state heat equation, this could be temperature. If you are trying to solve some problem in fluid mechanics, it could be pressure, it could be velocity. If you are trying to solve some sort of chemical reactions, it could look at species concentration. Now, the stencil method relies on trying to get information from the neighboring points. Essentially, what we are doing is that when we are constructing the approximation from the continuous PDEs, we are now writing equations or rather simultaneous equations dependent on the neighboring variables, and we are trying to solve for the unknown at each individual point. So, typically what will happen is that your numerical algorithm will now form a matrix equation of the form AU is equal to F, which requires solving. Now, you typically have to figure out what the inverse of this matrix is or try to come up with some iterative method with which I can then solve it. And these evaluations typically involve computing with the neighbors in the mesh, because you are trying to look at information around you and trying to figure out what the value at a particular nodal point is. So, when I want to solve this problem in parallel, the first thing that I need to do is sort of decompose this problem. By decompose this problem, I mean to partition it into hopefully equal sized workpieces. Because I am using a distributed memory machine, I have to send a portion of this particular problem to each separate machine where computations will take place, and I have to ensure that the workload between these different processes are more or less the same. Now, this is not an absolute necessity, but it's a good thing to have, because if different machines have different sizes of workloads, that means they will finish at different rates, and obviously the solution is complete only when the slowest worker is finished, which means the person who has the highest amount of workload finishes. So it's always a good idea to decompose this problem or partition this problem into more or less equal sized work pieces. So for a fairly simple geometry like a square, it is easy to partition these work pieces. You can use some sort of geometrical technique. That's what has been displayed here for this stencil problem. So we begin with the domain decomposition, and we have to first figure out what the parameters for this domain decomposition are. One would be the size of the global problem. Let us, for simplicity's sake, now assume that this problem is being run on a square, which makes our life of geometrically decomposing it easy. Let us assume that we have a total of px number of processes in the x dimension and py number of processes in the y dimension. So the total number of processes that I have is px into py. That is the total number of computing cores or distinct machines that I have access to. Now I am also hoping that if I take n, the size of the global problem, and if I divide it by px, the remainder is 0. Or if I take n and divide it by py, the remainder there also is 0. Hoping for this perfect divisibility typically means that I will have equally loaded processors. So I can partition this problem equally. If I do not get a remainder of 0, I will then have to unequally load these partitions, and we will talk about that in a later class. Now, assuming that the problem is regular, square, and nicely divisible, we will now get different partitions of equal size. We still need to figure out a few things. For each of the process, I need to geometrically figure out where I am, right? What is my position in the global geometry? I also need to figure out who my neighbors are, because when I'm doing sort of stencil communication, I have to now communicate with my neighbors certain information, especially at the boundaries. And there are two types of boundaries involved here. One are internal boundaries. What do I mean by internal boundaries? Internal boundaries are those boundaries which lie between two different processes, which are boundaries of communication only in a computational sense, or because they arise because we have partitioned the problem. For example, the green lines which are being depicted in this particular figure. The global boundary is the actual boundary of the physical problem, which is on the outside. So if you were to go back here and if you look at the boundaries which are not the green lines, but the boundaries which now I am sort of highlighting with my mouse pointer, that is the global boundary of the problem. That's where, from a physical sense, you will implement the boundary conditions for this particular problem, for its numerical approximation. Whereas the green boundaries actually represent internal points of the problem. If one were to solve this problem serially, these boundaries would not exist. These boundaries come in only because we have partitioned the problem and are now computing it in parallel. So we then parallelize these boundaries. So you have internal boundaries which are shown by the green lines, where inter-process communication is required, where we need to communicate between these two data members, and then finally the physical boundaries which are over on this side. So for the real boundary, I can obviously say that the process to which it needs to communicate is some sort of a null process. Let us say in this particular example, we have distributed this problem in 9 processes, 3 in the x direction, 3 in the y direction. We then have totally 9 processes. The process, we can number it as 0, 1, 2, 3, 4, 5, 6, 7 and 8. You will immediately notice that the process 4 needs to communicate the maximum with 4 other different subprocesses, whereas all the other processes typically are communicating with 2 and some of them are communicating with 3. In the next class, we will look a little bit more into this domain decomposition. Thank you.